Ladies and gentlemen, this PowerPoint goes over work and power, so please make sure you have the notes in front of you and are ready to write down the information. Please pause this video at any time when you need to write down information to make sure that you are understanding it. So let's start off with what is work? Well, the way you define work in your normal life is not the way that scientists define work. Most of you, when you hear the word work, think of a job, or cleaning your room, or doing some task where you may get money for it at the end, but that is not how scientists define work. Instead, scientists define work as whenever a force moves an object over a distance. So that means the force and movement have to be in the same direction for there to be work. So let's look at a couple examples. Which one of these, or are both of them, work? A teacher lecturing her class. Is that work? Well, let's think about it. Is there a force being applied? Is there motion? Because you have to have both of those things for there to be work. What about a mouse pushing a piece of cheese with its nose across the floor? Again, is there a force being applied? Is there motion? Because both of those things need to be true for there to be work. So if we look at this again, we see that the teacher lecturing is not work because she's not applying a force, and therefore there's no motion. So since there's no force, there's no work. But the mouse, on the other hand, is doing work. The mouse is applying a forward force on the cheese, and the cheese is moving in that same direction. So we have a force and motion. They're in the same direction. It is work. So let's look at some more of these examples. A scientist delivers a speech to an audience of his peers. Was there a force? Nope. Speaking is not a force. So is that force moving over some distance? Is it causing the object to move? Nope, because again, there's no force. So is it work? No, because there's no movement. There's no force. Let's look at the next example. A bodybuilder lifts 350 pounds above his head. Is there a force being exerted? Yes, upwards, because he's lifting it up. It's going over his head. There's a force. Is the barbell moving? Well, yes, it's moving over his head. What do you notice about the direction of those two? Are they in the same direction or in opposite directions? Well, they're in the same direction. So because of that, it has to be work, because the force and the movement are in the same direction. Here's where it gets tricky. If we have a mother carrying her baby from room to room, is there a force? Yes, she's holding the baby up. The baby's not on the ground. She's not pushing it along the ground. She's holding it up in her arms. If her arms weren't there, the baby would fall. So there is an upward force on the baby. But which way is the baby moving? So that force isn't being moved over a distance. The baby's moving left or right, whereas the force is up. So there's not in the same direction. So therefore, it is not work because they're not in the same direction. What about a father pushing a baby in a stroller or a carriage? Is there a force? Yes, it says pushing, so there's got to be a force there. And then usually your stroller is going to move in the same direction of your force. So we see that force is moving over a distance. So this is work. Force and movement are in the same direction. And the final example, a woman carries a 20-kilogram grocery bag to her car. Well, she's carrying it, so is she applying a force to it? Is she holding it up? Yes, she is. She's holding it up. So there's an upward force on that bag. But is there upward motion on the bag? No. So that force is not being moved over a distance. It's just one direction and not moving. So this is not work because the movement and the force are not in the same direction. Force and movement have to be in the same direction for it to be work. And we can calculate it using the formula force times distance. We then will measure this in joules, which is the same thing as energy. Please remember that energy is defined as the ability to do work. So they're actually measured in the same thing because they're considered the same thing scientifically. You can't have work without energy, and energy's purpose is to do work. So it's measured in joules. So please make sure you've written down force times distance on your paper where it says formula. And let's do a couple practice problems. If a man pushes a concrete block 10 meters with a force of 20 newtons, how much work has he done? 200 joules. And we know that because it's force times distance. So 20 is our force, 10 meters is our distance, 20 times 10 is 200. So he's done 200 joules of work. Again, please make sure you're pausing this video in between so that you can practice the problems and then check your answers. Don't just copy down. So same thing with this next one. Sam is picking up his groceries. He lifts the 30 Newton groceries up to his 3-meter tall counter. How much work did Sam do? So pause this video right now and do the math on your paper. So please remember that work is force times distance. So our force was 30 newtons, our distance was 3 meters, 30 times 3 is 90, so Sam did 90 joules of work. Is that the answer you got? If not, please make sure to talk to your teacher to see what you did wrong. J.J. Watt is a tight end player for the Houston Texans football team and is currently healing from a back injury. As part of his recovery, he works out every day using a weighted sled. If the sled weighs 1,372 newtons and he pulls it a distance of 30 meters, how much work did JJ do? Pause the video and do the math yourself. Remember that work is force times distance. So JJ had to apply at least 1,372 newtons of force to get this sled to move. So we multiply that by the distance he pulled it, which is 30. When you do 1,372 times 30, you end up with 41,160 joules. So that means JJ did 41,160 joules of work. We can also talk about how powerful somebody is because power is related to work. So power is the rate at which work is done, or it's how fast work is done. We can calculate this using the formula work divided by time. Eventually, you'll be asked to replace the word work or substitute the word work with force times distance because that's really what work is. It's the force times the distance. But for right now, let's just work on doing the work divided by the time. And it is measured in the unit of watts. So if you hear watts in your daily life, it's usually with a light bulb. And it's because light bulbs are actually doing work. They're moving electrons and they're moving them over a certain period of time. So a 60-watt light bulb does 60 joules of work every second, hence 60 watts. Let's go ahead and practice that. So if a light bulb completes 90 joules of work in 3 seconds, how powerful is that light bulb? Well, power is work divided by time. So our work was 90 joules. Our time was 3 seconds. So we are going to do 90 divided by 3 and get 30 watts as our answer. So a light bulb that does 90 joules of work in 3 seconds is only a 30-watt light bulb. It's not very powerful. Your normal 60-watt light bulb does significantly more work per second. Let's try another problem. Let's use J.J. Watt again. Please make sure you're pausing the video and doing the math on your own. So how powerful is J.J. Watt if he did 41,160 joules of work on the sled in 10 seconds? So if it took him 10 seconds to pull that sled and do that much work, what was his power? Please pause the video and make sure you've done the math. We end up seeing that when you divide 41,160 by 10, it winds up being 4,116. So JJ's power was 4,116 watts. Let's make this a little bit more difficult. Ben and Bonnie are in the weightlifting room. Bonnie lifts a 50-kilogram barbell over her head, which is about 0.6 meters 10 times in 10 seconds. Ben lifts 50-kilogram barbell the same distance over his head 10 times in 1 minute. Who did the most work? And who was the most powerful? So we actually want to see that they do the same amount of work because they're using the same force to lift the barbell. It's moving the same distance, so it's the same work. And then we're going to see that Bonnie is actually more powerful because she does the work faster.